Introduction. It's my pleasure to be on this platform to talk about my work. Let me see. I changed my title. Okay, changed to multi-object calibration of computationally expensive simulation models. That's because I think the work I talk about today is going to be suitable for any computer model, especially the computationally expensive model. Again, I want to acknowledge my co-author. I'm from Hohai University right now, but I used to work at Beijing Normal University. So those co-authors are my team members. So I want to thank them for all the great work that was shown here in this presentation. So talk about computer simulation models. Simulation-based science is a powerful complement to experimental science. So computer model is used in every imaginable field. Shown here are some of the examples. You talk about the simulation of underground nuclear explosion. Used to be, you can just explode a live bomb, and you can take all the measurements and to see if it works. But today, you cannot do that. You have to rely on computer simulation. Also, prediction of future weather and climatic events, the simulation of the underground water pollution, and the oil production from deep ocean oil reservoir. Also, I shown an example from the material science and engineering field, the optimal heat treatment for nickel titanium-based alloys. If you use experiment to do this kind of research, then it's going to be awfully expensive, and the computer simulation is a cheap alternative to accomplish that. So computer simulation solves two kinds of problems. One is the forward problem. Okay, the forward problem is predict the effect of a particular cause or causes. When talk about cause, the system forcing, the initial conditions, the model parameters, and the effect are the model observables. Usually, to run the forward problem, people start running the inverse problem first, because inverse problem helps you to quantify the uncertainty in the causes. Okay, so one particular kind of inverse problem is shown here. Okay, so you talk about parameter inversion problem. The so here is the illustration of that. And you have forcing, you have initial conditions, and then you assume some kind of parameters, and then you run your model, and you get something like this. I'm sorry why it's not the animation is not working anymore, but anyway, so the red line is the simulation, and when the simulation doesn't work, you run a optimization procedure to tune the model parameters, and then you get something more satisfactory. So the model calibration is referred to this thing, reducing the difference between model simulation and observation by finding the optimal parameters. So let's first define this problem. The mathematical formulation of the model calibration. First, here shown here is the mathematical expression of the simulation model. So you have y. T is the model observable, is the function of the initial state and the state variable and the inputs and the model parameters. Note that model parameter is a time invariant variable, and plus some noise. And so the mathematical expression of the model calibration problem is like an optimization problem. So minimization of this function of model parameters equal to the integration of the error terms. So the error is the difference between the observation and your model simulation, integrated over time. Also can be over space, subject to some kind of model constraints. Okay, the equality constraint, the inequality constraint, also explicit constraints on the model parameters, the lower and upper bound. So note that the function is both phase. That means it's a vector notation, and can be a scalar, a single objective function, but also can be a multi-objective function. So you have multiple objective function, become a multi-objective optimization problem. So let's first talk about single objective optimization problem, SOUPs. So the definition of that is to find the best or the optimal solution which correspond to the minimal or the maximal value of a single objective function. So this kind of problem shown here are some of the examples. You have this kind of problem is kind of relatively simple, okay? And then this here, okay, it's more complicated, and then here is the most complicated. And so the challenge associated with trying to solve this SOUP problem is, first of all, you have to deal with multiple regions of traction. Like in this case, you may converge to this place or converge to this place. And the thing is like we need to find this global optimal. And the second challenge is that you have to deal with many local optimals. In some cases, it's like uncountable number of local optimals, and through all the local optimals, you want to find the global optimal. And also, you have to deal with a rough response surface. In this kind of problem, you cannot calculate the derivatives because it's not smooth, and so making some of the methodology not available to use. And also the flatness, that means some parameters are insensitive, and it gives you this kind of issue, equifinality. Different parameters give you the same kind of objective function value, so making finding the global optimal difficult. Also, the shape can be a challenge. The non-curved ridge in response surface indicating high parameter interaction can complicate the search process. There are many different ways of solving SOUP's problem. If you look at the traditional classical textbook on optimization, there is a big category of methods. We call them local methods. One category is the gradient methods, which require you to compute the derivatives, the first derivative, at least sometimes second derivatives. This kind of approach can be very efficient, if it suits your problem. And then the second category of local methods is direct methods. This kind of method don't need to compute the derivatives, but maybe more funky variations compared to the gradient methods. Both of those local methods is local, that means can only converge to local optimal only. So it cannot meet our needs. So we have to work with global methods. In the beginning, a lot of people are working with so-called deterministic strategy. We really actually is using local methods. Before using local methods, they are using some kind of procedure like cutting plane methods, branch and bound methods, interval methods to eliminate non-optimal regions. That means you shrink the search space of the parameters, and then once you do that, then you apply some kind of local search methods to find the optimal. So this kind of methods has very limited use in our real world problems and not suitable for high dimensional problems. And over the last 30-40 years, this category of methods became very popular. Meta-heuristic methods. These kind of methods make use of the principles. We work in different disciplines, like in material science, the annealing process. Similarly, annealing allow you to find the global optimal, and the genetic algorithm, particle swarming, based on those kind of evolutionary principle. And I also highlight a method I'm going to talk about a little more. That's the method I developed many years ago. It's called SCEUA methods. Those kind of methods converge to global optimal asymptotically, but there is a but, require a high number of objective function evaluations. So it's not efficient. So let's talk about SCE methods. Stands for Shuffled Complex Evolution Methods, developed at the University of Arizona. So this kind of methods is motivated by genetic algorithm. Actually, make use of all those good features in genetic algorithm, the global search, evolutionary principle, genetic operators. But when I started working with genetic algorithm, it's very inefficient. It's taken a long time to converge. You have thousands of model evaluations to converge. So I decided to speed up. So how do I do that? I basically trying to make use of the efficiency of the local methods, the downhill simplex methods. Like in this case, like when you generate the offspring, you make use of this kind of like reflection, contraction, and etc. So allow the search to make use of the response surface information. And of course, in doing that, it can speed up, but also, I don't know if people heard of this principle. It's called no free lunch principle in optimization. When you speed up, it has a high chance of converging to local optimal. So I decided to solve this problem by extend the evolutionary principle by partition the population into sub-populations. So, the people say it converges to local optimal is because you have this genetic disease in the community. When you generate offspring, the inheritance of the genetic disease make it converge to local optimal. But if you break up into community, you allow this community to evolve independently, and then before you converge, you shuffle them. And that's where shuffling came from. And then when you shuffle them, you basically avoiding the pitfall of inbreeding in the community. So make it very, very robust. And this algorithm has been very, very popular in the hydrology discipline, and is very flexible. It's extendable to a different level of difficulty, the problems, and by choosing different algorithmic parameters. If you have a very complicated problem, high-dimensional problem, you can use more complex. And if it's a simple problem, you just use one complex. One complex is very similar to simplex kind of methods, very, very efficient, very, very fast convergence. But still, there is a limitation. It's not suitable for computationally expensive problems. Computationally expensive problem, I'm referring to the problem that you can take hours or even days to run one model simulation. So this kind of problem, we cannot use SCE. So we need to find a new approach for the computationally expensive computer simulation model. And one such kind of approach is called surrogate modeling based approach. And what is a surrogate model? A surrogate model, suppose like right now, here is a real world. Okay, there's a lot of physical processes going on in this real world. So we can use dynamic model to represent this real world. We can use all those grids, mesh points. Each of these mesh points, you have differential equations that describe the physical processes, and then you solve these equations numerically. And so this kind of thing can describe the physical process very, very good, very, very well. However, it's very expensive. So the surrogate model is doesn't try to emulate the dynamic process. Instead, it's trying to emulate the error response surface. Okay, so here you see, like, here is the error response surface of the dynamic model. And so if you have enough computation resources, you resolve each grid point, and then you can find a very good solution for the dynamic model. But the surrogate model actually don't want all the grid point, the mesh point, but using a limited sample, like here, those blue dots. On these blue dots, you run your model, and then you feed a surface in there. And this surface actually is the surrogate model. That's what we refer as surrogate model. And the solution of this surrogate model is the approximation of the dynamic model. So that's what we meant by surrogate model. So the process is like this. You generate the sample, use a design of experiment approach, a DOE approach. And if you know the response surface, you don't have any information on the response surface, then you on the parameter distribution, then you use a uniform sampling, like Lambda Haber cube, Lambda Haber cube, or use good lattice point, Sobel sampling, and etc. If you know the distribution of the parameters, then you can use some kind of spatial sampling. Once you have the sample, and then you run your model, and run your model through those samples, and then construct a surrogate model. And then you do an optimization on the surrogate model and get a solution. If this solution is good, then you are done. But it's not good, you add more samples. Okay, then you go through this process until you are satisfied to get, so once it's converged, then you get the best solution. So that's the kind of thing we use. And here, I present a surrogate model based methods we developed in my group is called ASMO, Adaptive Sort Gate Modeling-Based Optimization. Actually, here you're supposed to have some animation, but you cannot see it anymore. But you basically started with this gray line within the two model. You started with maybe those the sort gate model which like this, and then you add more points until you get a sort gate model which is it's you're satisfied. The solution here is the approximation of this solution. So that's what we meant. For this algorithm. So we tested this algorithm, compare this one to the SE method I just presented before. And this is a 6 objective kind of problem. And the blue here means it's not, it's not optimized. Here is optimized. So after optimization, you improve by like 9%, 15%, 15%, 9%, and except this one, okay. So you compare to the SE, the same thing, you improve to the same kind of degree. The difference is here, the ASMO method used only like 141 model runs. The SE method used close to 1,100 model runs. So we achieve the same kind of results with much fewer model runs. So that's the advantage of ASMO methods. So we talk about soups. Like soups is for single objective function, and even for the multi-objective, we convert it into a single objective function. Now we talk about a true multi-objective optimization kind of approach, solving the MOOPs. So the definition of the MOOPs is to find the best solution set, not a single solution, but a solution set with multiple objectives, which represent non-dominated solution. What we mean by non-dominant solution is like, you have this, this is the non-dominant period front. So if you want to improve like this objective function, and so you go this way, and then this objective function degrade. And if you improve this one, this one degrade. So that's the thing about, the multi-objective problem is trying to find this Pareto front. And so it has all the challenges faced by soup, but also, if you have more objective function, you also have to deal with the cursive dimensionality in terms of objective function space. So there are different methods available, and including the weighted sum methods I just showed in the previous example. And some other examples, some other methods, I don't want to get into the details, but here I highlight a category of methods. It's called evolutionary methods, the non-dominant, especially the non-dominant sorting genetic algorithm. So non-dominant sorting genetic algorithm, NSGA. This concept was first proposed back in the late 80s, and the first NSGA was developed in '94. But now this NSGA 2 is the one used by a lot of people. Even though it was proposed in 2002, today is still most powerful, most widely used multi-objective search algorithm. And this algorithm has a lot of strengths. Of course, it's well-known, fast sorting, relatively efficient, and suitable for both continuous variable and discrete variable. And it can also consider model constraints. But there's also a but. It needs a lot of model runs to converge. So here is a illustration of the difference of genetic algorithm and NSGA. So the procedure is the same. You generate a population, and then you compute the fitness value. But for single objective function, it's really easy. Okay. And then for multi-objective function, you have to compute for multiple objectives. And here is the difference. Here is straightforward. You just compare the value of a single objective function. But here you have to compute. You have to sort this thing. So non-dominated sorting is a key procedure, and also the crowding distance. Because when you find the Pareto sets, you want to have this property. The solution has to populate the entire front. So the maximal distance, you have to maximize the minimal distance between the Pareto solutions. So that's the two keys in NSGA. So we developed a surrogate modeling azimuth version of the of this thing. Okay, so here again, it's like you start with like sampling and then construct the surrogate model, and so you get maybe in the first one you get a solution like this, and then if you add more points, then you get the solution like this. Okay, so that's the illustration of this process, and we compare these two methods, the NSGA2 and the MO azimuth methods, and so here is the basically we blow up the Pareto front section. So both methods actually lie on top of each other. So in the sum of the function, you see it's very strange kind of Pareto front, and this one is like a concave instead of convex front, and so we get the same kind of solution, but there is a difference. You see, NSGA require 25,000 model runs to converge, and for MO azimuth we only need 800 runs. So we have a saving of close to like more than 30 times saving in terms of computational requirement. And recently we extended MO azimuth to constraint hybrid problem. That constraint is that you have constraints. You have to consider the constraints for your model, and also you talk about integrate hybrid variables. That means the decision variable can be continuous integer, also can be categorical variables. So that's the extension. So we extended to that. So there are two keys in there. One is how do we handle the hybrid variables. Okay, the hybrid variable, the handling of that, both the NSGA2 and the MO azimuth using the same kind of techniques. You mapping the continuous variable into integer space using a truncation kind of technique. And the constraints, there are some subtle differences in there. For NSGA, they deal with the constraints like this. Okay, if you have two feasible solutions, then you choose the one which has the best objective function. But if you have one infeasible, one feasible, then you, of course, you discard the infeasible solution and choose the feasible solution. If you have two infeasible solutions, then you choose the one with smaller constraint violation. But in the MO azimuth, we for objective function, we just use Gaussian process regression. For constraints, we use Gaussian process classification for binary classification, these kind of techniques. So you have two infeasible solutions. For this two, it's very easy. But if you have two infeasible solutions, we choose the one which dominates the other, ignoring the magnitude of the constraint violation. So that's the difference between the two, the NSGA and MO azimuth. So we compare these two, and before we compare them, we present two metrics for comparing MO, the multi-objective algorithm. So first is generational distance, GD. GD basically is compute the average distance of the non-dominant solution to some reference solution. Okay, so you average the difference. If the distance is 0, that means you have the ideal solution. Okay, and there is another measure is called honorary hypervolume. So you have this is the volume of your solution. Okay, then you compare to also the reference volume. This is the hypervolume, and so the ratio of this equal to 1. That's the ideal solution. If it's less than 1, then that means it's less desirable. And so we work with some problems. Maybe I think has some relevance to the material science and engineering field. So talk about design, okay, reinforced concrete beam design, or the pressure vessel design, or the coil compression spring design. So those problems come from the this reference, okay, Telabi and Ishibuchi, and we first talk about reinforced concrete beam design problem. And so this is the mathematical expression of that. And so let's look at the solution. Okay, so the black solid line is the true solution. Okay, and then here we use 300 model runs. We got the red dots here. Okay, that's the azimuth solution. And then here is the NSGA solution. This is the NSGA solution. NSGA solution. So you compare the two metrics. They have very similar metrics. Okay, in terms of honorary half volume and or the generational distance. And the difference is here. We use 300 model runs. Here use 2,500. So okay, so it's a saving of more than 8 times. And then the second example is the pressure vessel design problem. So here is the expression of this model here. Okay, I don't want to read through these mathematical equations, but here is the Pareto front. Okay, so the black means the true Pareto, and the red dots means our solution. And compared to the NSGA2, so here we use 500, NSGA2 use 2,000. So we get the same kind of solution. If you look at the statistics, they are very similar, and our distance is even smaller than theirs. And so this is another one, the coil compression design problem. So it's a spring design problem. And so again, so here is the MO azimuth solution, and here is the NSGA solution. So 500, 3,500. So you have very similar matrix. Here, we have somewhat smaller honorary hypervolume. That's because our solution actually is fewer than theirs. So our volume actually is a little bit smaller. And but the distance, we have much smaller distance to the reference front. Just one more kind of examples is the the water distribution design problems. So it's a two objective kind of problem. So one objective is related to cost, or other objective is related to the network resilience. And so this came from this reference, okay, Wang et al. And so they provided a set of standard test problems. And we didn't try all of them, but we tried some of them. I'm going to show 2 of them here, highlighted by this red box here. So you have the 2-loop network design problem. The number of possible solutions is 10 to the 9th power. And then the New York tunnel problem, the possible solution is 10 to the 25th power. And so so look at the 2-loop problem, and here is the MO azimuth. Okay, here is the NSGA2. So you talk about like 1,100, 4,000. So we got the same kind of solution. Actually, if you look at here, our solution is closer to the reference volume. So shown here, the distance is smaller, and the volume actually also we have better volume compared to NSGA2. So this is for the 2-loop network problem. And then if you look at the New York tunnel problem, here you talk about like they talk about how do you lay out those 21 pipes in 2 loops. And so the decision variable is the pipe dynamic size, and you involve 21 discrete variables. And there are many different pipe diameter options, 16 of them. So make it like 10 to the 25th power in terms of possible solutions. So we compare these 2 methods, and here is the reference solution. And the thing is this is like it's we can only get approximate solution. So here is the NSGA. When you run it 10,000 times, that's the best solution you got, is the blue dots. And then when you reach like 20,000, it gets to the green dots. Okay, And the red dots are the solution from MO Asmos, okay? MO Asmos. So you can see that, we have smaller distance, NSJ, we have similar distance, okay? We have a little smaller distance and the volume comparable. So we have 2,000 function model runs. They talk about like 10,000 to 20,000. So we have a saving of, like 10 times. So that's the examples I have shown here. Let me summarize what we have talked about today. So we have presented this surrogate model-based optimization approach for both single objective and multi-objective model calibration of computationally expensive problems. And so we described this ASMO procedure. It has a lot of promise, and we compare them. So the ASMO is just as robust as SCUA, but it's more efficient. And the same can be said when we compared MO ASMO to NSGA2. So you talk about like 800 compared to 25,000. And then lastly, we showed for constraint hybrid problem, MO ASMO is as robust as NSGA2, but it's 4 to 10 times more efficient. And there are a lot of potential for applications in a lot of other problems, including those kind of manufacturing design problem, reservoir operations problem, calibration of large complex distributed models, water system design problem, and etc. So I hope people look at this kind of approach. If you are interested, we welcome you to contact me. We can show how you can maybe using this kind of MO ASMO kind of approach for your own problem. And finally, I just want to show you that we have developed a software platform which incorporate all of those kind of techniques in there. It's not just the optimization, but also you have design experiment, you have statistical analysis, sensitivity analysis, and etc. So it's the open source software. It's called Uncertainty Quantification Python Laboratory, EQPyL, and you can download from this website. And we have a reference paper in environmental modeling and software. And finally, here is the list of publications related to the work we talk about today. Some of them already published, and there are some of them still in review. And also want to acknowledge my funding agencies. Okay, that's it. So this is my talk. I welcome any questions.